I think we get started now. Wow, it's crazy to see so many people here in this room. Wow, this is pretty exciting. Thank you so much for coming to our talk. My name is Lita, and this is Jose, and we're going to be presenting to you a case study of how Lyft is migrating over to Kubernetes, specifically on the networking side. So we'll be talking about how we're handling network traffic and how we're handling service discovery in this new Kubernetes world. There's many parts to a Kubernetes migration. So there's the deployment phase, as well as the provisioning stage and security groups, but we don't have time to cover all of that. So we're going to specifically be talking about the networking portion of it. So a little brief intro to who we are. My name is Lita. I really like boba, so that icon jives with me very much. I've been in the networking team for a year and a half now, working on many different things, but mostly on operating Envoy, and lately integrating Kubernetes with our service mesh and creating the networking portion of them, creating the migration plan for the networking portion. And I've been at Lyft for a long time, 4.5 years, and half of my time at Lyft I've been in product. I helped launch Lyft Line, and then the second half has been in infrastructure. So it's been pretty great to be able to take all my learnings from product and bring them over to infrastructure. Before Lyft, I came from a computer graphics background, so I worked at DreamWorks Animation, working on render farms and rendering algorithms, as well as making tooling for artists to ship out a movie, a children's movie, every year.
And my name's Jose, and I've been at Lyft and with the networking team for about 2.5 years. In that time, I've done a lot of I've dealt with a lot of aspects of our networking topology, all the way from the data plane to building out Lyft's new control plane platform, as well as being an Envoy maintainer.
So we've broken out this talk to 3 pieces. So first, we want to give you some context of why Lyft is doing this Kubernetes migration. Migrations are expensive. They take up a lot of engineering time, and they take up a lot of resources. So we want to explain why we decided to do this and what are the business benefits. Secondly, we want to give you context about our network topology is and what our service mesh is in the old legacy system, and then how we're transitioning it into this hybrid world of Kubernetes and our legacy system. And lastly, we want to share with you some lessons learned so that when you decide to do your own Kubernetes migration, you could take these lessons with you and take some of our learnings so you don't have to relearn them twice. So let's dive into it. So we're going to dive into why Lyft decided to do this migration in the first place. Because, again, migrations are expensive. It's easier just to maintain our legacy system. So what made us decide to pay this cost now at the size that we are and move over to Kubernetes? So I want to give a little bit of context business-wise. So Lyft is a very real-time system, and we usually can predict when our peak events are from historical data, but sometimes we can't always do that, right? So we have this, so there's a particular day I remember, the Mayweather versus McGregor fight. It was a boxing match, and it costs $100 on HBO to watch. And what tended to happen was people ended up gathering at people's houses to watch it and split the cost or go to a bar and watch it there. And after the fight was over, everyone requested a ride all at the same time to go home. And that is when everyone did that. Right? And it wasn't very something that we were aware of, because it was a one-off thing. It didn't happen historically before. It was also a nationwide thing that happened to be very popular, but we didn't have any historical data to predict that. And also, we in our legacy infrastructure, it's pretty expensive. We use AWS EC2 instances, and to launch that many instances, it takes around 20 minutes. So we couldn't scaling up fast is something that that's something that we struggle with at that bursty traffic. But and if we were to try to handle this beforehand, we would basically have to be over provisioned and then waste a lot of waste a lot of resources, like because we're not utilizing them efficiently. And that's what Kubernetes gives us, right? Like we're able to scale up pretty quickly and effectively use our resources so we can handle these bursty traffic scenarios. Secondly is we like that Kubernetes gives you a separation of concerns between your infrastructure code and your application layer. So right now in our legacy world, we have this folder called ops folder, and that's where all your orchestration files go. And also, like, you run a lot of infrastructure like processes on your EC2 box. So product engineers are the owners of these services, and they still have to be aware about what sidecar processes are running, as well as like maintain this like configuration code to like manage their like what instance type they're running, or like manage these like these launch configurations. And it's like something they don't use every day. They like want to program their application in business logic, and then once a month or once every like quarter, they like look at this and be like, oh, we need to scale. I forgot how to. Like, I don't know what these terms mean. I have to go look them up. So there's a lot of context switching happening here. And in Kubernetes, everything, all the in Kubernetes, everything runs in a container, and you just own your application container. So like they have a lot less things to think about, and all the infrastructure stuff can be run on separate containers in the same pod. So that's pretty powerful. Like that's what we want. We want product engineers to think about just their application and minimize the knowledge of infrastructure things that they need to do, and reduce that cognitive load. Lastly, the biggest reason is Kubernetes gives you this immutable infrastructure. Due to the fact that in our legacy infrastructure, due to the fact that EC2 instances take a long time to spin up, we can't deploy like rotating ASGs because then a deploy would take a really long time. It would take probably an hours or so. And so we value like being able to deploy and roll back very quickly. So we do upgrades in place. But there are some downsides to that. The one main downside is that the fact that your scale up code is not necessarily the behavior of scale up is not necessarily the same as your initial deploy. And with Kubernetes, because of the immutable infrastructure, you get the same no matter what. So when you do the initial deploy, it'll behave the same as if it were scaling up or scaling down.
All right. So taking into account the gains that we would see in a Kubernetes infrastructure, let's dive into what we have done from the networking perspective. So unless you're starting from scratch, you will end up in this hybrid scenarios where you might have legacy infrastructure and the infrastructure that you're moving to. And because we're real-time systems that can take downtime, we have to live these long migrations. So the focus that we want to do for the rest of the talk is how do we deal with this hybrid environments and this hybrid infrastructure? And the lens that we want to look at that through is the lens of a networking team, and more specifically, how do we do service discovery in this hybrid infrastructure? So before we start with where we are today and where we're going, let's take a look at our network topology up until now. Envoy is a project that came out of Lyft, and it is our networking proxy all the way from the edge of our infrastructure to all of our services to also egress out of our infrastructure. So what we have here really is a universal network primitive. All network traffic that flows through Lyft flows through Envoy. And this will become very powerful as we move into this hybrid system. We'll see how. Today, we're going to focus on the internal services that Lyft runs to run our platform. And this is what we have deemed the service mesh. So before I go into talking more about service discovery, I just want to do some level setting and briefly discuss what service discovery is. So in elastic infrastructures, as you may know, we have machines coming up and shutting down all the time. And so it is hard to pinpoint all the machines that in a stable manner, all the machines that might belong to a logical service. So what we do in service discovery is be able to pair particular hosts or particular IP addresses to a logical set of a service or an application. So for example, in the left, we might have 3 machines that are running a Python application, and all of these machines belong to service foo. Versus in the right, we might have, again, 3 machines that are running a Go service, and while there are 3 different machines with 3 IPs, they all belong to the logical service bar. So let's look at what service discovery looked at Lyft before Kubernetes. On the left here, we have, again, 3 services that might be composed of N or M machines. And on the right, we have our legacy discovery service, which is a simple Python CRUD service backed by DynamoDB. The machines in our service mesh run a cron job that every 30 seconds is registering the IP of that particular machine with a host of metadata. So the region that the service might be running in, the specific availability zone, the identity that it wants to pertain to in the mesh, so I belong to service foo, as well as, importantly, the IP address of that machine. That's the right side of our discovery service. Then on the read side, the sidecar Envoy that runs next to all the applications read discovery data from the discovery service. So this is how Envoy will know that for the logical service foo, these are the 30 IP addresses that belong to that service. And Envoy will be able to load balance requests from that service onto others in the mesh. So the desired end state that we have both in our legacy infrastructure and as we want to introduce infrastructure managed by Kubernetes is this simple flow of requests through the service mesh. So we want requests to flow through the sidecar Envoy regardless of what application it might be, or particularly where that resource might be, either in our AWS infrastructure or in our Kubernetes infrastructure. So this is the logical end state that we want, even though behind the scenes, we might have something like this, where all the resources that a service might have, might be in Kubernetes, or there might be another service that is all running in our legacy infrastructure, or even, and particularly interestingly, we might have a service that has both machines in our legacy infrastructure or in Kubernetes. So really the goal that we have as we move into this hybrid infrastructure is from the perspective of product engineers, we want to build a system that makes it easy for them to operate the network, regardless of what might be behind the scenes. So this is the focus that the networking team has had ever since we began. And particularly for Kubernetes, we want to make this new infrastructure accessible and easy to use, while at the same time maintaining Lyft's real-time system reliable. So in particular, for this migration, we have three goals. And on the left, we have the goal that we have for product engineers. This change, as we move to new infrastructure, has to be transparent to them. We can burden our product engineers with knowing the internals of our infrastructure. For example, when a product engineer wants to make a request to service foo, they shouldn't need to think about, is this request going to a pod managed by Kubernetes or to a virtual machine in AWS? The request should be transparent. They should just send the request, and it should be managed by the proxy. So while that's the goal that we have for product engineers, we also, as infrastructure engineers, have two particularly important goals to keep Lyft services and platform reliable. The first one is we want to design the system such that we can do an incremental rollout of this new infrastructure. And second, while we try to have the most reliable infrastructure and release it in safe ways, we also need to preserve the ability to roll back when problems occur. So before we delve into the solution that we came up with, I want to emphasize that what allows us to designed the system in the way that Lita is going to explain is the fact that we have this universal network primitive running alongside every single service at Lyft. Having Envoy as a sidecar next to every service abstracts the network from the service itself and allows us to do more sophisticated routing, regardless of where the resource might be. And specifically, what Envoy provides to us that allows us to do this is the set of XDS APIs that Envoy has described, which are a set of APIs that can dynamically configure the proxy from a centralized management server. So here we're separating the actual data plane that requests are flowing through from the control plane that might configure how that data plane is managing requests. So specifically for service discovery, Envoy has described and implemented the EDS API, which stands for Endpoint Discovery Service. Endpoint is just a specific entity that responds to a logical set of load balancing entities. So specifically, the XDS APIs are a set of gRPC APIs that from a central control plane can configure the data plane, and it separates the concern of configuration from actual request processing.
So I'm going to go dive into like the hybrid service discovery architecture that we came up with. So as you are from before, all the sidecar envoys running as separate processes are registering the IP address of that machine into the CRUD discovery service. But now we also have these Kubernetes clusters where we have multiple clusters, and there's a pod. We have services as pods, and they are sharded between many clusters. And we designed it that way so that if one cluster will go down, we could still, in Kubernetes, we can still serve traffic from the other clusters. And there's a Kubernetes API server that is aware of the state of the cluster. And so we migrated over to the Envoy XDS control plane, which is a Go service that has upgraded the configuration to the new XDS APIs. And it's pulling in data from the old discovery service and also making connections. It uses the Kubernetes watch APIs to get the IP addresses of each pods of that cluster, and then converts all that data into the EDS configuration and sends that off to the sidecar envoys. And now that they have that data, they know about each other, and they can start routing traffic to each other. And note here that in our Kubernetes clusters, there's no ingress controller. The pods are able to get an IP address that is aware in our VPC, and so that means that the legacy machines can talk to that pod directly. And there's many reasons why we went with this route. Unfortunately, we don't have time to go over why we went that way today, but if you want to talk about how we did that and why we did that, you could come talk to me, or my colleague Paul is here, and he will happily talk to you about how we made that possible. But yeah, so at the end of the day, because we are able to send those IP addresses out to all the sidecar envoys, they now form that mesh. Now there's no difference between the legacy boxes versus the Kubernetes boxes, and services can be split between Kubernetes and the legacy infrastructure. But at the end of the day, they get converted and merge and could serve traffic to each other. So this is great. So the reason why we went with this approach is because the change is transparent to the product engineers. They can still write application code and send a request, and Envoy will figure out how to route that request basically get a response back. We can now do incremental rollouts because we can, using Envoy's XDS APIs, we can set priorities. So we could put a lower priority on the Kubernetes clusters, or we can just scale up fewer pods, and then fewer traffic will go to those Kubernetes clusters. So we could slowly migrate old services over to Kubernetes in a safe way. And we're able to roll back as well. So there's all these kill switches we could leverage as such as like if let's say we roll out a bad Kubernetes change, we could fail health checks on the services on Kubernetes, and then all the traffic will be routed to the legacy infrastructure. As well as we could just scale down and then in Kubernetes, and the traffic will still get routed to the legacy infrastructure, which is pretty powerful. So we'll go over the lessons learned as we started this process. There's 4 main lessons that we want to share with you as we went through changing our service discovery over to this hybrid system.
So the first one that we want to talk about is eventual consistency. Is it friend or foe? So the way that service discovery works in Envoy is it's an eventually consistent system where it's the ability of a particular envoy to route traffic to another envoy is based on this matrix, where it depends both on the data that the discovery system is sending via the EDS API, but also based on the health check status between one envoy and the other one. So as you can see here in this table, only if the health check is passing, then Envoy will route traffic to that particular box. And importantly, only if the health check is failing on a particular host and that host is not being delivered via the discovery system, Envoy will prune that data out of the set of hosts that it load balances traffic to. The reason why this is particularly important in this migration is that let's suppose that our discovery system, as we move into this hybrid ecosystem, has a bug and can deliver hosts for the Kubernetes clusters. If Envoy has already known of those hosts in a previous deploy of the discovery system, then Envoy will still have that host in its local knowledge of the mesh, even if the discovery system is failing. This allows us to more reliably and more confidently deploy changes to our discovery system. Why I say it might also be foe is that because we have an eventually consistent discovery system, as we roll out changes, changes are not impacting the entirety of the topology at once. These changes take time to roll out, and so as an operator, when you're deploying changes to your service mesh, you might expect that metrics change more rapidly than they actually do. And so you might have to be able to monitor and think about problems not immediately, but in the long term as the mesh converges. Another important lesson that we discussed as we were embarking on this migration is what I tried to describe as the golden egg problem. It's kind of like Indiana Jones, where you're taking out the rock and you're taking out the golden egg and putting the rock, although hopefully we're doing it in the reverse order where the new system is the golden egg. But what this really means for us is that we can take downtime and we can just have maintenance modes where we're shifting our infrastructure into first this hybrid environment and then into the end state. We have to do it as we run the service. So the beauty and the power of having this universal network primitive is that we can do this migration in ways that we can control how traffic is slowly shifting from our legacy system into our new system.
The final 2 lessons we've learned is that having unified observability is very powerful. The fact that we have a service mesh and we have envoys running on all the pods and all the legacy machines, we can actually compare apples to apples. So like as we roll out to Kubernetes, more services to Kubernetes, we can have comparisons of like how quickly does these pods spin up and like what are the rate of changes, and we could also have a unified language and to observe like such as like network, network requests coming in, as well as 500s and 400s. And also, what's really nice is that we can use existing dashboards and we can tune our alarms to easier as we migrate over to Kubernetes. And secondly, we can de-risk our migration, and we have protection against like things not going perfectly in our Kubernetes migration. Like nothing's going to go perfect. Like software is going to fail, and the biggest thing is that we can migrate faster because of the fact that we have the service abstraction of the service mesh. We can, by this I mean like we can load balance at a finer grain level and like ship traffic slowly to the new Kubernetes pods as they spin up. And we can also fail health checks on the Kubernetes clusters if things are going awry and quickly route traffic back to the legacy infrastructure. And Envoy has really great retries policies, so in the end, there should be no degraded experience for the end user. And this is honestly because we've migrated over to the service mesh early on, and we're not paying the dividends to do these like risky, to do these like kind of big migration, not risky, but big migrations like Kubernetes. And that would be, I don't think we would have this much of an easier time if we didn't migrate to the service mesh in the first place.
So, well, today we've talked about service discovery and, in a larger sense, the network team. This hybrid infrastructure, as I said previously, is something that happens for any type of migration, for any type of system where you're moving from a legacy infrastructure to a new infrastructure. While today we've only talked about Kubernetes and our legacy virtual machines, the principles here of maintaining a hybrid infrastructure can apply to other topologies like multi-cloud or multi-tenant. That is all that we had for today. So thank you very much for coming, and we have some time for questions. I think we have about 5 minutes for questions.
Yeah. There are no questions.
Yep.
Yeah.
I have a question about the matrix where, like, when you
Yep.
take the first of the cluster, did you experience any issues with, like, draining requests or connections?
So the question was, in this eventually consistent discovery model, did we have any issues with draining connections? Do you mean draining connections as we fail health checks?
No, like as you have, like a host you want to deprovision, you like stop announcing it, it's still up, and then you just kind of turn it off, even while it's still taking requests.
Yeah.
So yeah, go ahead. You can.
Yeah. So the rest of the question is, say you have a host that you want to deprovision. It's still part of the discovery set, but we take it off of the health check. We start failing health checks. We're still taking requests on that connection. So active health check in Envoy works with certain parameters. We have it such that you health check on an interval, right? And so when that health check starts failing, Envoy will drain the connection. So it will still finish the requests that are in flight, but it will not accept new connections to that particular upstream. So any other requests that might have happened to that logical cluster will be load balanced to other healthy endpoints. So this is one of the reasons why, as we migrate to a new infrastructure, we're able to fine-tune traffic in a very granular way. Yes?
You mentioned one of the benefits is that you get better scaling, and then you don't have to spin up all these extra AWS instances, but what are you actually doing to scale the underlying cluster that all the pods are going on? Because like, that's presumably running on some VMs somewhere as well that have to be scaled in advance?
Yes.
Right. So
repeat the question.
Repeat it. So the question, I believe, if I understand it, is how do you deal with the scaling of the clusters as well? So from that perspective, I think provisioning is coming up with a plan to scale up, like make sure that there's like a pool of nodes. So there are always going to be resources available, and then like and basically there should be enough. If as more pods spin up and there's less nodes available for resources, they start scaling up. So we're getting ahead of it, right? By like, so there always going to be a pool available for more workloads, and that's provisioning's job to make sure that they're always going to be enough nodes available to launch more pods onto the Kubernetes cluster. And then there is an issue of like, if we start routing all this traffic back to the legacy systems, how do we handle that? We just have to overutilize. We have to over provision at that point in the legacy infrastructure to handle that.
But isn't that essentially the same problem that you had in the first place?
Right, but like the idea is that that's a short-term cost as we move over to Kubernetes, right? Like that's what we're doing now, essentially.
Yes. Yes, so the question is, how does this topology of the hybrid ecosystem relate to the front proxy? So the front proxy is also reading discovery or EDS data from the XDS control plane. So it's essentially the same, right? The front proxy has, for example, a logical cluster foo, and within that logical cluster foo, we might have endpoints that are in Kubernetes or in the legacy system. So the same way that the service mesh discovers particular hosts for particular services, the front proxy is using the same system. Mm-hmm. Any other? Yep. The question is, do we have any plans to use Istio as our control plane? I have a full talk on control planes. My basic answer here is control planes are very opinionated. I always describe them as a service in three parts, and the front part of a control plane is munging your infrastructure's topology into the XDS APIs. For Lyft, in particular, because we carry the history of Envoy with us and a very, very opinionated topology, it makes no sense for us to, at this point, massage our infrastructure and our topology into Istio's way of service discovery, of route configuration, of cluster topology. So that's why we built our own control plane. One of the reasons. I can talk at length about this, so if you're interested, we can talk more.
So with like a legacy deployment model, usually you have some kind of mechanism to deliver the route and application, kind of like an F5 load balancer, you can down and disable members and whatnot. And one of the struggles I have is if you get into a cloud environment and you're trusting health checks, what do you do in like the event of like kind of a grave failure where you know something's wrong, you're not actually failing health check, maybe it just hasn't been hardened or configured properly? Do you have some way of basically actively routing by forcing your health check to fail? Or?
So the question is, in this environments where we're relying on health checking to actually doing traffic shifting and popping endpoints out of a logical service, how do you deal with gray scenarios where an endpoint might be not responding correctly, but it might still be responding health checking? That's where Lita was talking about. The power of the EDS API is that you can specify, for example, load balancing priorities. So we might, as network operators, open up an API in our control plane that can say, okay, mark this endpoints as unhealthy, not by failing health check on the machine itself, but by delivering discovery data that says, this has a priority of, -1,000, so that traffic will not be routed there. So that's one of the ways that having this topology has de-risked this migration, because we have several, checks and balances or flags that allow us to shape traffic the way that we want. Mm-hmm. I think we are at time. Thank you so much.
Thank you so much
we'll
for
be
coming.
Here.